Well, good morning, good afternoon, or good evening, depending on where you are in the world, and welcome to today's DevOps.com program, brought to you by Techstrong and Redis. My name is Cody J. Brown. I'm the host of Techstrong Learning, and we have an exciting program ahead. First, I just need to cover a couple of housekeeping notes. So today's session is being recorded. If you miss any of our discussion, or maybe you'd like to rewatch or share with a friend, the on-demand recording will be made available shortly after we conclude our live session. If you have any questions, and we really hope that you do, we want you to send those in to us using the Q&A tab, which can be found on the right side of your screen. We'll try to address as many questions as we can toward the end of the program, so please do send those in as soon as you have them. Also on that right side of the screen is where you will find the chat tab, and that's where we want you to get to know your fellow audience members. Let us know your thoughts throughout today's program, or maybe just from where you're tuning in. We do have a poll that we'll be launching here pretty shortly into the program toward the beginning. So we do want your participation there. And if you navigate to the handouts tab, you'll find a whole bunch of resources that Redis has made available for you for today's program. So the topic of discussion today is overcoming the challenges of deploying microservices data layers on Kubernetes. And I'm joined by Alan Terletto, Field CTO of Redis, and Lars Rosenquist, Manager Partner Solutions Architect at Redis. So Alan and Lars, thank you both so much for joining me. Alan, do you want to get us kicked off?
Yeah, thanks, Cody, and thank you all for joining us. My name is Alan Terletto. I'm the Field CTO here at Redis. Today, we'll talk about overcoming deployment challenges of the microservices data layer, specifically when deploying them at scale with Kubernetes, and how Redis is uniquely positioned to reduce that complexity across dev and ops. But that's not all. We're not just going to talk about it. We'll show it to you. And for that, I'm joined by my colleague, Lars Rosenquist. Lars will demonstrate how Redis Enterprise can be used on Red Hat OpenShift to deploy a handful of microservices backed by Redis databases in order to compose a retail banking application we call Redis Bank. Lars' demonstration will be comprehensive. It's going to be informative, and I think you're going to enjoy it. So let's quickly set the table for him and dive right in. Let's begin with the what. What's driving seemingly every organization to consider or already begin their migration towards microservices? Where did all this momentum come from? To answer this, sometimes it's helpful to take a step back and observe all the other things that are changing around us. For example, even before COVID-19, offices began to change from siloed cubicles to open spaces. Our approach to project management changed from traditional waterfall models to agile methodologies. Infrastructure changed. Deploying software on virtualized and containerized environments is now the norm, with many organizations migrating to the cloud. Now, these changes didn't happen overnight, and they did come at a considerable cost. So the real question is, why are companies investing towards this transformation? Well, it's complicated, but if we had to reduce it down to a single answer, it would be time to market. So why time to market? Well, as we barrel towards a digital-first economy, the competitive landscape and expected customer experience is drastically changing and at a rapid pace. In fact, some analysts claim that it was accelerated by a decade due to the pandemic. Startups with limited resources are disrupting entire industries from the bottom up. Big tech is leveraging their vast economies of scale to encroach into new lines of businesses from the top down. Digital native scalers are feverishly launching new products, and a new generation of technically savvy consumers are no longer loyal to brands. So for many traditional enterprises, these are systemic level risks. Kicking this down the road is no longer an acceptable option, as they did for over a decade. It's time to modernize. It's time to improve business agility. So what's still holding back organizations from improving time to market? Didn't easy access to infrastructure and adopting a DevOps culture solve that? Let's break it down. We've seen a commoditization of infrastructure over the past couple of decades. The cost of DRAM is at an all-time low, and CPUs have improved by orders of magnitude, seemingly every few years. In fact, infrastructure can now be provided as a cloud-managed service or through a PaaS. We can even package our preferred OS, platforms, applications, and configurations into a container and deploy it with an orchestration platform. Brilliant, right? However, while easy access to infrastructure is critical to agility, in a vacuum, it's still not enough. For example, with taking a legacy monolithic application, packaging it within a container, and deploying it with Kubernetes, let's say on the cloud, actually improve time to market? suppose it's possible, but from my experience, doubtful. So maybe it's time to address the monolith itself and how we've gotten here. According to Conway's law, the structure of software will mirror the structure of the organization that built it. In other words, if the organization is siloed, its code is going to be siloed. If the organization has communication problems, the application will have inter-service communication problems, so on and so forth. And as it stands, most enterprises still have a traditional hierarchy composed of large departmental silos. Although these departments do have separate teams that work on separate business functions, it is often the case that their work product is packaged and deployed as a single application. For example, an e-commerce website, which is scheduled for deployment based on a common release cycle. It's this monolithic interdependency and the common release cycle which stifles time to market. So now we've identified root cause. So what's different about microservices? Well, in a microservice architecture, we decompose that monolith into fine-grained, independently deployable services so they can go to market on their own release cycles. According to Martin Fowler, Chris Richardson, and other gurus on this subject, successful microservice architectures typically keep with the tenets of isolation, empowerment of autonomous teams, and embrace of eventual consistency for communication. Well, that's great. Well, that would certainly improve time to market, which was our goal. But how do we now operationally manage potentially hundreds or even thousands of isolated microservices? Well, before we explore that deeper, and Lars demonstrates it for you in depth, let's pause here and take a quick poll of the audience. Since many of you are practitioners, we would like for you to share where your organization has stumbled the most with their microservice deployments. I'll give you all a minute to enter your answers, and we'll show you the poll results before Lars's demo. I'm going to cue the music here. This is about the closest I'm ever going to get to Jeopardy, so I'm going to enjoy this. All right. Thank you all for participating. Since we won't have those results for a few more minutes, let's see how your peers answered as part of a recent study by IDC called the Impact of Application Modernization on the Data Layer. The study found that microservices have gained wide adoption, reflected by 89% of respondents acknowledging that their companies are at least in the early phase of scaling out the architecture. Furthermore, 24% of microservice applications are already considered to be mission critical, of which 42% would directly result in revenue loss if they suffer downtime. But as we know, it's not without drawbacks. The migration to a microservice architecture significantly impacts the data layer. According to the IDC, a more distributed data layer creates challenges in deployment workflows and system-wide management of differing service SLAs and SLOs. As you can see, survey respondents chose database management as a major challenge for their microservice applications, which can be mainly attributed to managing traditional databases on today's cloud-native platforms and infrastructure. Hence, an overwhelming 84% of respondents are already using a NoSQL database to support their microservice applications. Let's double-click on this, as they say now, so we understand why. If you look at the diagram in terms of its lineage, relational databases and mainframes originated during a period not only before clouds were a viable idea, but storage, particularly RAM, was very expensive. With that as the constraint of the time, databases were optimized primarily with disk-based storage in mind, not performance nor data access. This has commonly caused what is known as an impedance mismatch between the way we store data within columns and rows and the way we access and visualize it as objects or documents or time series, etc. So not only was performance limited by the physical constraints of a spinning disk, which hasn't really improved much over the years, but the extra transformation, serialization, and complexity to overcome this impedance mismatch limited performance across both latency and throughput. Now, fast forward to today's unprecedented demands for large-scale, simultaneous access to real-time data, and it's no wonder we're seeing outages during volatile market peaks and hampered digital transformation efforts. However, this is where NoSQL databases shine. NoSQL databases were built using a 180-degree different mental model than relational databases. While relational databases optimize for storage first, NoSQL databases optimize for data access first, which avoids that impedance mismatch. They were also built in the 2000s when storage became increasingly cheap, including RAM, which allowed for the viability of distributed data platforms to further drive down the cost and set them up perfectly for the advent of managed services on the cloud. So where does Redis fit into this? Redis is an open source, in-memory, NoSQL database, which natively supports a variety of data structures and data models that are each natively designed for peak real-time performance and high throughput use cases across transactional, operational, and analytical workloads. Redis was originally popularized for being the fastest data store in the market, with its sub-millisecond performance, its ease of use, and more recently as a multi-model database, a perfect fit for modern-day applications and microservices. I'm sure everyone watching this live or on demand already knows about Redis. However, if you missed our recent announcement, you may not have heard about Redis Stack. Redis Stack consolidates the capabilities of the leading Redis models into a single deployable package, including JSON, time series, graph, Bloom filters, and Redis search for secondary indexing and SQLite querying. It also packages our development visualization tool called Redis Insight and our supported set of Redis clients called Redis OM or Redis Object Mappers, with support across the major programming languages. This allows developers to have everything they need to develop with Redis end-to-end, minimize installation friction, and improve the overall operational experience. But what if you wanted to store more than a small set of ephemeral data that can neatly fit into a single Redis process? While Redis is often used as a cache, it has the capabilities to be your primary store for session, authentication tokens, market metadata, inventory, ML features, and other critical data. But this requires the ability to scale out its deployment and introduces the needs for coordination between many disparate Redis processes. And you probably want to do this across distributed infrastructure in a way that is seamless to the application. So what started with ease of use has now evolved into building a distributed database. Suddenly you're researching the CAP theorem, learning about the different nuances of each consistency model. Did you know there's more than two? Dealing with replication channels across unstable networks. And clock drift. Wait, what's clock drift? All of this is extremely complicated. And wait, there's more. Now that we built our distributed Redis database, we'll want to share it across our organization. Recall that in a microservice architecture, each bounding context should operate in isolation so it can go to market on its own release cycle. This means that every microservice can have its own database, and there's going to be many, potentially hundreds. So we'll need to create a Redis as a service offering to our organization, which allows each database to independently scale, horizontally and vertically, so we can optimize the use of the underlying infrastructure. Of course, we should make scalability and upgrades dynamic, so we don't need to incur unavailability as the business grows, or we incur peak transaction volumes. Also, we'll need to meet system-wide SLAs, which can include up to 5 nines availability guarantees across active-active geo-distributed deployments with built-in conflict resolution. All of this with portability and support on Kubernetes environments and one or more clouds. So what do we do to overcome these deployment challenges? Of course, this is where Redis Enterprise comes in. After many years and hundreds of thousands of deployments as a native cloud service, we decided to package our battle-tested knowledge of how to best manage Redis in a cloud-native environment into software called Redis Enterprise that can be deployed by our customers on-prem, on Kubernetes, as a cloud-managed service, or even as a first-class SaaS offering. Redis Enterprise provides enterprise-grade operational capabilities, such as linear scalability, high availability, durability, backup and restore utility, security, and more uniquely, capabilities such as multi-tenancy, active-active geo-replication for business continuity, and tiered data storage to reduce total cost of ownership. Speaking of unique, as mentioned, we've extended the foundation of the open source project so Redis can become a multi-model database. As you can see on the top right, Redis Enterprise supports the native storage and query capabilities of multiple models, such as JSON, time series, graph, Bloom filters, and secondary indexing to support SQLite querying, everything that's within Redis Stack. Putting it simply, if your application plans to access mission-critical data as JSON, then just store it as JSON. If you need a time series, then use a time series model. No more impedance mismatch, just optimal real-time performance and faster time to market. So let's now explore how the many concepts we just covered converge to compose a microservice architecture. We know that microservice practitioners favor isolation and NoSQL database. While this has its advantages, it can quickly lead to a seemingly complex architecture. But as the slide says, Redis can simplify this. Let me take you through it step by step. I mentioned that Redis Enterprise is a multi-model database, which means each autonomous team is empowered to choose the optimal model to store and access their microservices data. While this might sound like a great idea at the 10 microservices scale, it can become a daunting endeavor for operations as the deployment grows to hundreds or even thousands of databases. However, this is where Redis Enterprise's multi-tenancy shines, by allowing each database to be deployed on the same cluster, so all models benefit from the same enterprise-grade capabilities in a uniform way, without breaking the tenet of isolation. Now, Lars is going to demonstrate this in just a bit. Redis can also seamlessly consume and publish telemetry data using its streaming and time series data models. If you recall, observability was the #1 challenge identified in the IDC survey question. So this is a critical component to success as you scale out your microservice architecture. Redis's streaming technology can also be used as a distributed publish-subscribe message broker and event source store. This can enable reporting, analytics, auditing, or even forensic analysis on the back end. And Redis can even provide data integration between isolated services, so transactions can cross bounded context using choreographed sagas and CQRS using our change data capture capability. If you are interested to learn more about using Redis to implement these patterns, check out the Newstack blog on how Redis simplifies microservice design patterns. To sum it up, all of this is possible with a single cloud-native platform, Redis Enterprise, which significantly reduces the complexity and overhead of managing a portfolio of vendor technology, which, as mentioned, comes with complicated deployment challenges and barriers to improve time to market. Finally, infrastructure automation and orchestration, another critical key to success as you scale out your microservice architecture. As you can see from the IDC study, 99% of respondents are using orchestration to deploy microservices, which really only begs the question of who was that 1% and how are they doing? So here again, Redis Enterprise can simplify operations with our native Kubernetes integration, which can run on vanilla Kubernetes, OpenShift, VMware Tanzu, GKE, AKS, and more. In lieu of being redundant with Lars's demo, I'll leave you with the high level that Kubernetes Operator manages Redis Enterprise cluster nodes, as well as supports a database controller to manage databases via custom resources. We also support Terraform for infrastructure as code deployments and Vault integration for secrets management. Both are beyond the scope of this talk. However, it felt like something this audience might be interested in. Anyway, without further ado, let's circle back to those survey results and bring in Lars, who will walk us through the deployment of a microservice architecture using Redis Enterprise on Kubernetes. The floor is yours, Lars.
Thank you for that amazing introduction, Alan. So let me start my part of the presentation, and I will start by sharing my screen. All right, so there was a lot of concepts introduced by Alan, and there was a lot of material there. And I think the best way to show some of these things in practice by showing an actual application. Alan already mentioned, we've got an application called Redis Bank. Redis Bank started out its life cycle as being a monolithic application. It's an example of a modern real-time retail banking application. Of course, it's a demo application, so it won't be as feature-rich as a real modern banking application. But still, there's a lot of interesting features there that we're going to show in a couple of minutes. As the application progressed through its life cycle, we've modernized it a little bit and also turned it into a distributed microservices application. So what does that mean? So what you see on the screen is a screenshot of the application. And don't worry, I'm going to be showing the real thing within a couple of minutes. And what you can see there in the application is it shows a bunch of data that you might also find in your mobile banking app, like general account data. There's also some personal finance management items like balance over time or your biggest spenders, where's your money going. There is, of course, a real-time transaction overview and the ability to search. And what I did for the microservices part is to split this in a couple of components. So first of all, there's the UI component, basically displaying the website, running the JavaScript, but also aggregating information from various microservices. There's about a handful of services in there. So there's one for the account management, there's one for the personal finance management, and there's one for the transactions. How are we going to be deploying that? Let's take a look, because I created a little bit of an environment. And to start out with the environment, I created 2 environments because I'm going to show off, of course, also the streaming and the active-active capabilities. So I've got one environment, and I'm going to be deploying that on my IaaS provider of choice. For both Red Hat OpenShift, which I will be using as a Kubernetes distribution, as well as Redis Enterprise, it doesn't really matter what the cloud provider of choice is, as long as it's a supported one. So today I'm going to be picking GCP. But it could have also been Azure or AWS or something like VMware Tanzu on premises or in the cloud, whatever is your preferred way of your preferred IaaS of choice. What I then did is deploy my Kubernetes distribution of choice, and my choice for today is Red Hat OpenShift. On top there, it's one of the distributions that's supported by the Redis Enterprise Kubernetes Operator. And the reason I like platforms like OpenShift, but also VMware Tanzu, is because they're not just Kubernetes distributions, but they also bring a lot of value out of the box in terms of, they're more on the PaaS side of the spectrum, platform as a service, which means they also offer a lot of components out of the box that you're going to need to build anyway or maintain. So you can choose to build or put those together yourself using other distributions, or you can buy a platform or maybe consume a platform that already has it out of the box. But that said, you can also deploy the Kubernetes operator on, let's say, GKE or AKS or EKS, whatever. Once the cluster is up and running, I'll be deploying the Redis Enterprise Kubernetes Operator. And as Alan already mentioned, after deploying that, it will enable a couple of custom resource definitions. One of them is the Redis Enterprise cluster. So you can use the Kubernetes API to create a Redis Enterprise cluster inside of OpenShift in this case. What it also does is it also exposes a custom resource definition for the Redis Enterprise database. So you can also use the Kubernetes API in order to create and manage the lifecycle of Redis Enterprise databases. That's, of course, very interesting, but I'm going to be doing this on 2 environments today. So I spun up another environment, also on an IaaS provider of choice. In my case, I chose GCP again, but a completely separate environment. But it doesn't have to be the case. These don't have to be the same. If you're going to run Redis Enterprise in active-active configuration, you can also mix and match cloud providers. So you can do a GKE in Azure, or a GCP in Azure, AWS and Azure, or maybe you have an on-premise environment based on VMware Tanzu or some other provider that you want to connect to your cloud. Again, I'm going to be deploying my Kubernetes distribution of choice here. And another reason to, let's say, pick another Kubernetes distribution on top of a cloud is because it means that now you have only one Kubernetes distribution to manage. It's an extra skill compared to what's available on the cloud providers. But if you're managing multiple Kubernetes environments, you don't have to worry about having all these skill sets available in your organization. And you can use, for instance, the same one that you're already are using on premises, for instance. Again, I will also be deploying the Kubernetes operator and a Redis Enterprise cluster there. And up until this moment in time, these environments are completely separate. But not for long, because I have deployed there an active-active database. And an active-active database that I'm really using as this Redis streams message broker, because this is indeed a stream, and a stream is a data type in Redis. And this stream is being synchronized via Redis Enterprise, via a concept called conflict-free resolution data types, or CRDTs for short. And they will make sure that you can do both reads and writes on both sides of the fence, and that the data will be synchronized. And there are some design choices that I made here that I will explain later on. So I will be deploying my apps scattered across these environments, but also some of these microservices have databases of their own. And that's a common practice when you're designing microservices, is that microservice have a database of their own that they don't necessarily share with other applications. So the Pfm service, for instance, will have a Pfm database that contains the time series module, as well as a sorted set to store the Pfm data. There's the transactions database that will store bank transactions and also allows Redis Search to be able to index and search them. And there's the account database, which will also use Redis JSON to store the accounts. So if I'm then going to be deploying the application with its different modules, we're going to deploy the Pfm service, the transaction service, and the account management service, as well as the UI. And one of the things that you can see here is that this Pfm service, even though it's consuming the stream and taking the transactions and the events that are coming in from this stream, and processing and analyzing that data and putting that into its own database, it also means that if the stream is ever interrupted for whatever reason, maybe there's a downtime issue, or maybe your Redis Enterprise cluster is down, or your Kubernetes cluster is down, or your entire cloud is down, or a region in the cloud is down, the application itself can still work because its own database is still available. And of course, you can distribute these across the different environments as well. Now, where does all the data come from? I'm not a bank. I don't own a bank, because if I were, I wouldn't be here. So I wrote a little application that generates test data and bank transactions, and I'm going to be deploying that over here. And this is going to generate a bank transaction, put it on the stream. Redis Enterprise will take care of the synchronization. These applications will consume it. And yeah, it's all going to look very lovely. Of course, to show that we can also do writes on both sides, I'm also going to be deploying the data generation app on the other side as well. So you can see that we can do reads and writes on both sides of the fence. All right, let's take a look at the actual application, and let's see what that means and what that will be doing. So for that purpose, I will be going to the terminal. Within my terminal, I have two tabs. As I mentioned, there are two environments, environment number 1 and environment number 2. So I'm keeping environment number 1 in tab number 1 and environment 2 in tab number 2, just to keep things pretty simple. How do I do that? Essentially, I've set up an environment variable that sets my kubeconfig to the file kubeconfig over here. And on the other side, I've done the same, but it's pointing to kubeconfig 2. So they're pointing to two different environments. All right, so the first thing I'm going to do, and I'm going to start at the application side of things, and I'm going to be starting at the second environment, because that's where I'm going to be deploying some of my applications. So let's take a look at the files that I will be using to actually deploy this application. As you know, if you're working with Kubernetes, you're going to be doing a lot of YAML, and this demo is no different in that sense. So I took a 3-tiered approach to the application in this demo. So for every app that I have here, I have a deployment file, which describes a Kubernetes deployment. I have a service file, which describes the service needed to access the application. And I'm also deploying an OpenShift route in order to be able to provide ingress so you can access the app from my MacBook in this case. OpenShift routes is one of the ingresses that's supported by Redis Enterprise. We also support Nginx and HA proxy. That will also work perfectly fine on OpenShift, by the way. You can totally deploy that and do that. But like I said, OpenShift has a lot of components out of the box, and this is one of them, and that's why I prefer to use them. So let's take a quick look at the application deployment file before we're going to deploy it. It's a pretty standard Kubernetes deployment file. So we give the application a name, number of replicas. In this case, it's 1. I'm also not putting any constraints on CPU usage or memory usage or things like that. Of course, you in your production environment would definitely be doing that. We're going to be pulling a container image, which is the image that I built earlier. These are all Spring Boot applications. By the way, in the documentation, you can also find the GitHub repo to all these applications and also documentation on how to use it. So feel free to check it out. We'll be exposing it on a port that we've given a name. And then we also provide some configuration for the application once it's deployed. Now, one of the cloud-native best practices that I've learned over the past few years is that typically you don't bundle environment-specific configuration with your application, because environment-specific information can change. And you don't want to rebundle your application all the time. And you might have different environments, and you don't want to bundle 6 different files with your application. So cloud-native practice here is that environment-specific configuration is injected into the application at time of deployment or dynamically if the framework and the platform support that. So in this case, I've put some environment variables in my deployment file. So in this case, the UI app needs to be able to connect to some other applications and also to the stream in this case. Of course, having it in this file kind of just moves the problem. So if I have a different environment, I'm going to have a second file that has different parameters. So there are different ways in Kubernetes to do that. So one way is with a config map or with secrets, or perhaps you're using something, a third-party product like HashiCorp or Vault or something like that. So there are different options, but for now, I've put them in the deployment file. The service file is pretty uninteresting because it's pretty bog standard. We take a look at the route that's being configured. So that's an OpenShift route, and you can also see it at the API because it's OpenShift. I'm going to be telling where the application is going to run, which host name. I'm also doing some TLS termination. So my application doesn't support TLS because I didn't build that in. But because OpenShift has this routing mechanism in it, and it also provides TLS termination, it means I can still say that I do not want any unsecured traffic, so HTTPS only. And I'm terminating it at the edge in this case. So in this case, inside OpenShift. And I'm connecting this to my service. All right, let's deploy this application and then see what happens. So we're going to deploy this application. And we're also going to be deploying the, let's say, account management app. And let's also deploy the transaction app. So that should do a couple of things on the screen. No, maybe not everything already, but let's take a look. If we take a look at the pods, these applications start pretty quickly. Again, is another cloud native best practices. So when we talk about microservices or micro applications, we don't want applications to take 3 or 4 minutes to start. So a couple of seconds at most, because the Kubernetes scheduler can intervene, and you're going to have to do things with timeouts, etc. So either refactor those old applications or maybe don't deploy them on Kubernetes because they should be deploying in a matter of seconds. All right, let's take a look at what happened because it looks like all my pods are up and running. So if I take a look at the UI where previously no application was present, and I'm going to be starting it now, and it's presenting me with a login screen. In this application, I'm using Spring and Spring Boot. I'm also using Spring Session, which uses Redis to start a session in its local repository. So even if you scale out your pods or scale down your pods, or you have to upgrade them or they're being moved around, your users will still be able to access the session as long as they have the sufficient credentials in order to access it. Now let's take a look what happens if we log in. So we are greeted with a screen, and some information is populated, but not all. But that's, of course, correct because I didn't deploy everything yet. So there's some general information that's being populated. The transaction information is being populated. I can also search this. So I can search for, in this case, the description, or I can search for some other things, and Redis will search that. You can see it's pretty quick. That's because this is, of course, all indexed, and it's all in memory. So it can serve that information pretty quickly. The Pfm data is really not showing yet, but that's, of course, logic because I did not deploy that yet. So let's do that now. So let's also deploy the Pfm application in this case. And what I'm also going to be doing is on the other clusters, look, I'm switching tabs, and I'm also going to be deploying the data generation app. And I'm going to be deploying that over here. All right. By the way, for the data generation app, I did not make a service and a route because the data generation app has no UI, so it doesn't need to have an ingress or a route available. And now you can see I'm not using my hands, but transactions are starting to flow in on this side of the application. You can also see things happening in the Pfm part of the application. So the balance of over time is being filled. We can also see the big spenders being updated. So that data is all coming in. And yeah, what's really happening now? Because I deployed a lot of the applications on the second part of the cluster or on the second cluster, while the data generation app is running on the first cluster. So the data generation app is generating a bank transaction every 10 seconds, and it's putting that on the stream. And every time there's a new element on the stream, the UI app, who's also subscribed to the stream, will push that information into the UI. That's why you will see it updating in real time. But it will also force an update of the other data that you're seeing on screen. All right, let's take a little bit of a look at what the application, what makes the application actually tick. All right, for now, I'm gonna stop the data generation app. So let's do that with a delete dg-app.yaml. And then for a moment, let's take a look at what is needed in terms of infrastructure to make this all work and to make the diagram in the slides work. Again, there's a whole lot of YAML there, so I'm going to be starting at the bottom. The first thing I did was deploy Red Hat OpenShift. I did not use Kubernetes to do that. I used the good old command line and a virtual machine. So I spun up a virtual machine in Google Cloud. I downloaded Red Hat OpenShift installer, and I just kicked off the command line and let it install. I'm not going to do that in real time because that takes about 30, 45 minutes. That's a long time. But again, it's a PaaS, so there's a lot of components to deploy. And if you want to do that in a high available way, so with 3 instances each, that's going to consume a couple of resources, and it's going to take some time. All right, so after the Red Hat OpenShift cluster is up and running, we can start deploying the Kubernetes operator. So how do you get the Kubernetes operator? Well, the best way to get the Redis Enterprise Kubernetes operator is by going to GitHub. So you can get it over here. You can also go to our website and then browse the website and then get a link from over there. Both of these will have the documentation that you need to deploy the Redis Enterprise Kubernetes operator. And also it shows you all the configuration and all the things that it can do. All right. Let's take a look at what's needed to deploy the operator. So I cloned the GitHub repo right over here. And when we take a look at the files, there are 2 important files. One is the OpenShift.bundle.yaml, and the other is the bundle.yaml. The only thing that you need to deploy the operator and have a predefined configuration is to deploy one of these files. This one if it's OpenShift, and that one if it's not OpenShift. Again, this uses a couple of features for OpenShift specifically. That's why it's a separate file. But you can just apply the file just like you do any Kubernetes file. And after that, the operator will be available on the environment. And you can see that because there will be a couple of pods running that are called Redis Enterprise Operator, as well as a couple of other things. Now, once the operator is up and running, like I said, it introduces 2 new custom resource definitions. I have a whole bunch of other things, but I'm going to be talking about these 2. So the first thing is the Redis Enterprise cluster. So, and let's take a look at what is needed to deploy a Redis Enterprise cluster. If we take a look at configuration that's needed, we can see that there's now a type here, or a kind, a Redis Enterprise cluster. Giving it a name, we're also giving it 3 nodes. Now, nodes here is a little bit of an overloaded word because in this case, it means Redis Enterprise nodes. It doesn't mean Kubernetes nodes. So in the non-Kubernetes world, a Redis Enterprise node is typically a virtual machine and will have a number of shards running on it, which are Redis processes under the hood. But in Kubernetes, our nodes are pods. So if I create a cluster with 3 nodes, it will create actually 3 pods within Kubernetes. I'm also telling it where to find the images, which in this case come from the registry at redhat.com. And I'm also specifying some parameters for the active-active setup. So if you want to have 2 clusters operating in an active-active way, you also need to be able to, they need to be able to communicate with each other. And that's why you need to tell them or expose a URL for that purpose. So I'm doing that in public right now, but typically that's maybe that's not something you want. So especially if you have private networks between environments, that's probably a better option there. But for this demo, I'm using a public one. And again, I'm using the OpenShift route. Again, you can also use another way of ingress here, like HA proxy or Nginx. But over here, we're using OpenShift route. So every time an active-active database will be created, it will use these APIs to communicate, and it will also create a database with this suffix so that the other side knows where to find it. Again, this takes a couple of time, a little bit of time to deploy, so I'm not going to do that in real time. But after you've deployed the cluster, you will see a bunch of pods being created, as well as a bunch of services with which you will be able to interact with the cluster. Essentially, there are 3 ways to interact with the cluster. You can use the operator, which use the Kubernetes API. You can use the REST API, or you can use the UI. That's also an application that's running on one of these pods. So you can also do a graphical user interface and configure everything there, just like in regular Redis Enterprise. There's actually a number 4. You can also do the CLI. So if you log into one of these pods, there's also the command line interface that's also available. So that's also something that you can use. But after the cluster is up and running, yeah, you're going to have to create a database. So if I'm going to take a look at what we have to do to create a database, it's a pretty similar story. So if we take a look, for instance, at the transactions database, that's one of the microservices running on my environment number 2. You can see that there's now a kind of Redis Enterprise database. I'm giving it a name, in this case, TR2 DB. I'm specifying a memory size, and I'm also specifying that I want to enable the TLS mode. Because contrary to my applications that didn't support TLS, Redis Enterprise does support TLS. So we're going to terminate the TLS in Redis Enterprise rather than in OpenShift. I'm also specifying that I want a couple of modules added to this database because, like I said, I wanted to store the transactions natively as JSON, and I want to be able to search and index them. Now, of course, how do you know which modules are supported by your Redis Enterprise cluster? One way to find that out is by saying a kubectl describe and then the name of your cluster. And it will give you a whole lot of information. It went a little bit fast, but there's a whole lot of information, including all the Kubernetes information and a lot of statistics. But it will also show you all the modules that are installed and their names and their versions. So these are the names and the versions that I'm also going to be using to deploy the Redis Enterprise database. All right, so this is all pretty cool and stuff like that. But in the end, the magic is in the active database. At this moment, creating an active database is not yet supported by the Kubernetes operator. It is something that we're working on, so that will be released at a later point in time. So right now, you can do that either via the REST API, the UI, or the command line. And after you have created an active database, in the end, it's pretty similar to creating a regular database, except you also have to specify the participating clusters and a bunch of connection info. But after you have done that, we can connect to this database, and that's what I'm going to do. So I'm going to connect to the active database on my first cluster, which is defined by large rhost1 on this side. And I'm also going to connect to my active database on the other side, also using the CLI. And then we can sort of start interacting with this cluster, right? So this is cluster number 2, and this is cluster number 1. But it's the same database, and data types are synchronized between these environments. So I can do something like set hello devops.com, right? So I'm setting a key called hello to the value of devops.com. And if I say get hello, it will say devops.com. But on the other side, I can do the same. I can say get hello, and it will say devops.com. But maybe I don't want it to read devops.com. Maybe I want it to read redis.com instead. And then if I go to the other side and I say get hello, it will now read redis.com instead. Now, this database is also the one that I'm using for the transactions. So it actually has a key called transactions that contains all the transaction events. And I can get all the information out using this command. Xrange is a command that's used to get a range of elements from a stream. The transactions is the name of the key. Minus stands for the first element, and plus stands for the last element. So if I get all the elements out in the stream, and of course, this is a demo environment, so the stream is not very large, so this will be done very, very quickly. You can see all these elements in there, all these transaction information being exchanged between these environments, and they are present on both sides. Now, imagine that your app goes down for whatever reason, or maybe the stream is interrupted, etc. So you can choose to do what I did over here. You can say sort of, hey, give me all the elements in the stream. So you can always reconstruct the history in the past based on the stream. But you can also say something like xrange and then transactions again, and then the ID of a key. So this is ID of one of the elements in the stream. And then I can say, hey, give me all the elements from then until now, which, well, obviously, because I turned off the data generation app, it's only going to give the element that I'm specifying because these ranges are inclusive. But it does mean that whenever you have an interruption in the stream or your application goes down, etc., as long as you maintain the last ID of the last element that you read, you can always reconstruct this. And it improves the resilience of your application a lot, because the application will have their own local database where they manage their own local information, and they can subscribe or resubscribe to the stream whenever it's present there or not. So even in the case that there's a downstream issue, your users can still use this banking app, even though the information is not up to date. But the app is not going to be completely down. It's going to degrade in a graceful way. And that's, I think, is a good thing. All right, I think this is about the information that I had to show at this moment. So I'm going to take a look at the questions or some of the poll items that are there, and then see if we can start answering some of that information and see if there are any interesting questions out there.
Hey, Lars, I'm seeing a question. It reads, what's the difference or the similarities or advantages of Redis streams versus Kafka, K-A-F-K-A?
Yeah, I think in general, sorry, maybe Alan wants to answer this. Sorry, I saw you answer.
No worries. Let me just kind of introduce streams real quick, and then I'll hand it over to Lars as well. By the way, we have an entire ebook on Redis streams. If you guys do want to check that out, you could easily find that. I think the easiest way to compare Kafka and Redis streams is going down to thinking of the Kafka topic partitions as the equivalent of a Redis streams key. And you still have the full benefit of consumer groups, having multiple consumers on that stream, having a time-ordered event log, in the case of Redis being completely in memory. So there is a lot of parity in what you can do from a publish, subscribe message broker. And you saw me allude to that in that microservices diagram. You want to add anything to that, Lars?
Yeah, absolutely. So there are obvious similarities and also certain differences between Kafka and Redis. It's also worth mentioning that Kafka and Redis also play nice together, for instance. So we often see them used in situations at our customers where these things are being used together. So yeah, I think there's a lot of value regardless of whether product you're choosing or whether you're going to use both of them.
And just to add to that, well, actually, I think it's in next week or in a couple of weeks, we'll be speaking at Current 2022. So we'll be demonstrating some of that integrated capability that we have with Kafka Connect, moving data into Redis, and then being able to visualize that data. So if you guys are going to be attending Kafka's summit called Current now, you can check out our session there.
Perfect. Our next question reads, hello, how did you create the original Kubernetes cluster? Did you use Terraform or other infrastructure as code tools? Thanks.
That's a really good question. So I'm one guy who made a demo, so I did it by hand. I strongly advise you not to if you are in an organization and you're going to be dealing with a lot of applications, right? So some of the customers that I'm speaking to, they deploy not one application, not 10. No, they deploy 10,000 or 15,000 different applications. They are also not putting them in one cluster. So I know there's let's say two kind of streams in the Kubernetes community, sort of a one cluster and then separate via namespaces, or have a multi-cluster approach. I think that if you want to maintain some level of boundary, especially on security front, and limit the blast radius of, let's say, service outages or any security incidents, etc., a multi-cluster approach is good. I would also not recommend you to create one cluster for every application, right? So you're going to have not, let's say, 10,000 clusters, but you're also not going to have one. So in that case, I would definitely use an infrastructure as code tool. So if you talk to Red Hat, they will probably tell you to use Ansible or something like that. However, if you want to use Terraform or some other infrastructure as code tool, that's of course also perfectly fine, and depends really on what you're using in your own organization. So if you're using Azure DevOps pipelines, for instance, you can also integrate with that or some of the other tooling that you already may have. Maybe you are using Ansible or some other tool, etc. But I would definitely recommend you to automate the lifecycle of your clusters, and also do the same for your Redis Enterprise clusters and your Redis Enterprise databases. As you saw in the demo, the YAML there is pretty simple and pretty standard. So if you can maintain that separation between having those deployment pipelines and the configuration that goes in it, you should be able to automate that with, let's say, a minimum footprint. And as you scale up, you don't get bogged down by all that management overhead that you're going to have to do. And it's also error prone, right? So I would definitely recommend using something like Ansible, Terraform, or Azure DevOps pipelines, or whatever it is that whatever is your weapon of choice in that.
So are Redis streams similar to Kafka streams?
Yeah, I think we just kind of covered that. Again, I think the best way to look at it is that the Kafka topic partition is the equivalent of a Redis stream. So it just sounds like something we already covered.
All right. We've got another one. So what are best practices around managing configuration for deployed applications on Kubernetes?
Can you repeat that question again? Sorry.
Just what are the best practices around managing the configuration of deployed applications?
Yeah, absolutely, right. So what I showed in the demo, I mean, it's great for one man and one user, but if you have more than a couple of applications, more than one environment, that using that, let's say, environment variables in a file is typically becoming a mess. So you want to manage that configuration in a different way. So Kubernetes Secrets or config maps are a way to do that. Some of the things that I've also seen in a lot of customers, especially if they have very large environment, is that they use some kind of third-party management tool for that. So you can use something like HashiCorp Vault. But if you go to the large cloud providers, they will usually have solutions for that to be able to manage those credentials in a way that is much easier to operate than just putting them manually in files. Again, you will have to create some automation around that probably to make that work. But I would typically recommend using one of those solutions, especially if you start using it at a bigger scale, because in the end, you want to do things like credential rotation, and you want to, let's say, maybe services are moving around, especially in a multi-cloud environment. They might be living in one way, in one location one day, and in another the other day. So you want to have the flexibility around that by just changing a value somewhere and then forcing a redeploy or a re-roll out in Kubernetes, and then the information is all updated.
Awesome. So I'm going to give our audience just another minute or so to send in any more questions they have while I give away a couple of gift cards. So these are for 4 $25 Amazon gift cards. Our 4 winners are Damon L, D.W., Safia D, and William N. So to our 4 winners, congratulations. Keep an eye on your email inbox to claim that gift card. But if you don't happen to see that email, do check your spam folder. I'll also take this opportunity to remind everyone that this session was recorded. So following this program, you'll receive an email with a link to access that recording on demand, or you can find it, as well as all of our other on-demand programs, living on devops.com/webinars. All right, so let's check the banks again. Did we receive any more questions, guys?
Yeah, I think I see a new one. Let me read it. Are there sync connectors in the Redis messaging ecosystem to connect Redis message brokers to NoSQL databases like Cassandra or MongoDB? So we actually support our own change data capture platform. We call it Redis Connect. And what that allows us to do is seamlessly integrate with the transaction log or outbox table on the source side. So we support multiple relational databases, and we also support, to directly answer your question, MongoDB as well. We've had demand for Cassandra in the past, but not a lot. So that's something we would look into. But yes, we support files, we support relational databases, and we support NoSQL databases in order to seamlessly migrate that data from the source and having Redis as that target. And actually alluding back to that Kafka Streams question, if you want to actually do any kind of transformation within Redis itself, kind of like you would do with Kafka Streams outside of that Kafka layer, our Redis Gears capability is a server-side compute engine, which can allow you to do kind of functional programming and allow you to have that business logic. So you can basically listen onto a stream and then perform some kind of transformation within Redis itself.
All right. And so it looks like we didn't ever touch on the poll results from the poll we launched at the beginning of the program. Do you guys want to dive into that?
Yeah, absolutely.
We've got our results live on the screen.
All right. So the challenge is, if I look at the poll results, some of them are grouped a little bit closer together, but the number 1 here is building, refactoring applications in a cloud-native way. This is typically also where we see a lot of our customers struggle or figure their way out in their cloud-native journey. Especially what we see, I mean, I'm going to take sort of the typical enterprise, and maybe it's a bank, and they have a very large application landscape. And some of those applications are very old. So they've been around for 45 or 50 years or even longer, and they're living somewhere in the basement of the bank, typically on a mainframe or other systems like that. But they also, at the same time, have very modern applications like you would find in your mobile app. So they have very modern applications as well that are built on modern technologies. And typically, you also find different sort of cadences or life cycles if you go to the departments. Remember Conway's Law? So we see that these applications in the basement of the bank, and they're old, but make no mistake, they're not going to throw them away because they're making them a lot of money. So these applications are not going away anytime soon. On the other hand, we have these application teams that are using very modern techniques and modern applications that are acting very quick. So they have a very quick time to market because they can move very quickly. At the same time, you need to connect these layers using something like Redis because these old applications don't support the modern throughput and latency requirements that those new modern applications have. So we can see there that in the application landscape, there's a lot of what I call low-hanging fruits that you can start building and refactoring, and sometimes without too much trouble, immediately start deploying in a cloud-native environment like Kubernetes. But there's also a lot of applications that will take a lot more time, also because these applications are a lot more complex. There were a lot of reorganizations in the organization. Sometimes documentation or testing frameworks, etc., are non-existent at all. So obviously, these are going to be a bit harder. And before I worked at Redis, I used to work at a company called Pivotal before it was acquired by VMware, and application modernization was one of the things that we did. And typically, we analyze the portfolio upfront and then start moving immediately all the workloads that are, let's say, the low-hanging fruits that are easy to migrate. And then at the same time, define plans for what you're going to do for those old applications. And sometimes that means turning them off. Sometimes that means keeping them as is, or sometimes things can be rehosted so you get at least some of the value. But yeah, like I said in the demo, if you have an application that takes 3 minutes to start and has a lot of in-process information and you're going to be deploying that on Kubernetes as is, you are probably not going to be happy. You need to do something about that. And technologies like Redis can help with that a lot. At the same time, I do think that this is an exercise that I would recommend start small, start doing that with a couple of, like I said, low-hanging fruits, start applications, build up some experience with the platforms that you're building out. Don't try to do everything all at once, but build those flying hours, as I say, build up the experience so you, get the experience in the platforms and the technology that you're using, and then start using that built-up experience and do the more difficult applications.
Well, we are at the top of the hour, so I do want to give Alan the chance to leave any closing remarks if you have any.
No, I think, Lars kind of just wrapped it up beautifully. And I think that's the value proposition here for microservices where, when we think about moving to the cloud or application modernization, it just could seem really daunting. You've heard me use that word in the past. And where microservices really shine is you don't have to convert your entire architecture in a single day. You don't have to have a 3-year project in order to see some outcome. There's a pattern called the Strangler migration pattern or application pattern, where you can literally break off that monolith, as Lars was mentioning, little by little, get that muscle memory, get that strength as you progress onto new technologies. And you can even use technologies like CDCs to integrate with your existing architecture and your existing legacy platforms with a technology like Redis. So you can have things like blue-green deployments or even hybrid deployments, or essentially have these systems of record deployed for many years until you have that comfort level to finally break off. So I think Lars kind of wrapped it up perfectly, and it really talks about how we can have these microservice architectures at scale. And of course, you saw the demonstration in terms of how we can manage that new pain, a new good problem of how do we actually deploy this at scale.
Awesome. Alan, Lars, thank you both so much. And I'd also like to point out that under the handout section, there is an ebook that goes into the streams, the difference between Redis streams and Kafka streams. So please do download that ebook. It is available in the handouts tab. So to our audience, thank you all so much for joining us. To Alan and Lars, thank you. And to Redis, thank you so much for sponsoring today's program. We do appreciate everyone spending their time with us today. And I do just want to mention that we have a survey that will pop up on the screen as soon as we close out that we'd really, really appreciate your participation in. Other than that, we hope to see everyone at an upcoming Techstrong Learning program. Have a great rest of your day.
Cheers.
Bye-bye.